an AI-generated post for your viewing pleasure. In the complex world of multi-agent systems, achieving both convergence to a stable Nash equilibrium and minimizing individual regret has long been an elusive goal. But a groundbreaking new study has cracked the code, introducing a game-changing algorithm that delivers on both fronts, a remarkable feat that could reshape the future of strategic decision-making in everything from traffic management to resource allocation. Imagine a bustling city where autonomous vehicles navigate the roads, each driver pursuing their own interests. Despite their individual goals, these self-interested agents must find a way to coexist and optimize the overall efficiency of the transportation network. This delicate balancing act lies at the heart of multi-agent systems, a field that has captivated researchers for decades. At the core of this challenge is the concept of the Nash equilibrium, a stable state where no individual has an incentive to unilaterally deviate from their chosen strategy. Reaching this equilibrium is vital for ensuring the system's long-term stability and performance. But there's a catch. In the real world, where agents have limited information and must adapt to a constantly shifting landscape, simply converging to the Nash equilibrium is not enough. Agents must also minimize their own regret, ensuring that their choices remain optimal even as their competitors change tactics. Cracking this complex puzzle has proven to be an elusive goal until now. A groundbreaking new study has introduced a novel algorithm that simultaneously achieves convergence to the Nash equilibrium and guarantees sublinear regret for each individual player. A remarkable feat that could revolutionize the way we approach strategic decision-making in multi-agent environments. At the heart of the author's breakthrough is a variant of the Frank-Wolfe algorithm, a celebrated optimization technique that has found widespread applications in machine learning and game theory. But this is no ordinary Frank-Wolfe algorithm. The researchers have infused it with two key innovations that set it apart from previous attempts. First, they've introduced a carefully designed exploration step where each agent intermittently mixes their current strategy with a uniformly random distribution. This strategic exploration ensures that the agents gather sufficient information to learn the optimal strategies, even in the face of a constantly changing environment. Secondly, the algorithm employs a recursive gradient estimator, which ingeniously reuses past gradient information to reduce the estimation error. This clever technique enables the algorithm to converge to the Nash equilibrium at a faster rate than previous methods, which often relied on additional projection steps that added computational complexity. The result of these innovations is an algorithm that not only converges to the Nash equilibrium at a near-optimal rate, but also guarantees that each individual player will experience sublinear regret, meaning their choices will remain close to optimal, even as their competitors adapt and change over time. The author's breakthrough builds upon a rich history of research in multi-agent learning, where the quest to balance convergence and individual regret has long been a central challenge. Previous attempts have relied on various strategies, such as regularization, projection-based methods, and more complex gradient estimation techniques. However, the author's algorithm stands out by striking a delicate balance between these approaches. By combining the simplicity of the Frank-Wolfe method with the power of recursive gradient estimation, the algorithm achieves a level of performance that surpasses prior state-of-the-art results. Notably, the author's work on Markov potential games, a stochastic extension of the traditional potential game, represents a significant advancement in this domain. Their algorithm improves upon the previous best Nash regret bound from OT56 to OT45, bringing the convergence rate closer to the optimal theoretical limits. Moreover, the author's ability to achieve these guarantees without requiring knowledge of the distribution mismatch coefficient, a parameter that can be challenging to estimate in real-world scenarios, further enhances the practical applicability of their approach. This flexibility is a testament to the elegance and robustness of the underlying framework. The groundbreaking research presented in this study has the potential to reshape the way we approach strategic decision-making in multi-agent systems. By introducing an algorithm that simultaneously converges to the Nash equilibrium and guarantees sublinear regret for individual players, the authors have addressed a long-standing challenge in the field of multi-agent learning. The implications of this work are far-reaching, with applications spanning domains as diverse as traffic management, resource allocation, and even social network analysis. As autonomous systems become increasingly prevalent in our daily lives, the ability to reliably coordinate the actions of multiple self-interested agents while minimizing individual regret will be of paramount importance. Through their innovative combination of the Frank-Wolfe algorithm, strategic exploration, and recursive gradient estimation, the authors have presented a powerful tool that could unlock new levels of harmony and efficiency in multi-agent systems. As researchers and practitioners continue to push the boundaries of this field, the insights and techniques introduced in this study are sure to serve as a guiding light, inspiring the next generation of breakthroughs in the complex and fascinating world of multi-agent learning.